Let's keep talking about how pointers and functions are interacting together. Okay, one of the things that we said early on was that functions, well, as their mathematical equivalent, can return values. Okay, so we had example of function, for example, sum, returning an integer. Okay, let's write a function named myFunction. No parameters to keep it simple to start with, but instead of returning one of the primary C language data type, we're going to return a pointer on int, for example. Okay, so let me write the code for my function here. I need to return the address of something, so I'm going to do something which is really wrong, something which is exactly what I want to illustrate in this video. I'm going to return the address of a local variable inside the function. Okay, and this is, I would say, it's probably a common novice C programmer bug. Okay, we are just going to illustrate here why it's such a bad idea, and we're going to trace the stack diagram to show you exactly what happens when you write this. Okay, inside the main, I'm going to call my function. All right, so I'm going to say, well, here's a pointer on int. This pointer is going to be assigned whatever my function is returning, which is the address of an int, and then I'm going to display on the screen, of course, this is my int value, and I expect, of course, to display, to dereference PTR, to display what is inside that int, which address I have. And you're going to see how vicious this kind of bugs can get. Alright, let's get rid of syntactical errors. Well, of course, the compiler is already, warning me here about the fact that I'm returning the address of a local variable. So it's no fair. I should have turned off some of the warning, because this is like way too easy. But let's try to run it and see what happens when I run it. This is an interesting bit. Okay, I bypass the warning, I ignore the warning, and I'm still trying to get this to work. What I would expect is, since this is a bug, since this is an error, I should actually have the program crash when I'm trying to dereference here an address, which is pretty much an invalid address. It's the address of the int TMP, but this int TMP doesn't exist anymore because I returned from the activation record corresponding to this invocation of my function. So why is it that the program is still displaying a correct result? To understand that, we need to do a stack diagram real quick, and I need to explain something which I have been pretty much bypassing until now. Okay, what happened exactly to activation records when they are removed from the stack? All right, let's start with a basic stack diagram here. Okay, this is my program execution stack. As always, text, data, BSS segment fused together here. This is here the system information corresponding to my entrance to the main activation record. I have a pointer, a local variable of data type pointer inside the main, named PTR. Initially contains null. Then I call my function, so that means that I'm stacking here another activation record. It is the system information, such as return address. I have a local variable here, no parameters, but a local variable TMP inside my function. This is an integer containing 42. And let's say that this variable TMP is located at a memory address, which I'm going to call alpha. When I execute return address TMP, well, address TMP is an expression. Okay, I apply the address operator to the variable TMP. That returns to me alpha, the value alpha, the address at which TMP is located. My function is done. Okay, so and this is where we need to be a little more careful. So far, I've been telling you that the activation record disappears. Okay, well, it doesn't really disappear. It's just something called the stack pointer, which tells me pretty much where the top of my stack is located, is going to be modified as I return from the function, so that instead of pointing here to the end of the activation record for this function invocation, it's going to point here at the end of the previous activation record. So for all intents, that means that this activation record here is not supposed to exist anymore. It's not supposed to be used anymore, okay? Anytime in the near future I'm going to need a new activation record, I'm going to start building up here. So I'm going to push new information on the stack here, overwriting what is here. However, by moving the stack pointer here, I pretty much intended to discard what was on the stack, to pretty much say, well, from now on I don't use it anymore, so I'm ready to overwrite it. But I didn't overwrite it yet. So this means that right now in memory, when I return from my function, guess what? TMP variable, the system information are still on the stack. They are not meant to be used anymore because they are ready to be overwritten at any time. Okay, but imagine that you have a sort of ghost persistence here, a ghost image of what used to be on the stack, which is still there. Okay, I didn't wipe the stack in the sense of resetting every bit of this activation record here to 0 to destroy the information. So what happens? You return the address of TMP. Okay, you use it from the main to take the sorry, so I should have put alpha here, I forgot. But when you return the address of TMP, you assign it to PTR here in the main. Okay, so alpha is now in PTR, which means that PTR is pretty much said to be pointing to the variable TMP, which no longer exists, but I still point to this memory space. Okay, this memory area. So what happens when I do a start PTR and I try to dereference PTR and pretty much display what's in this memory location? I still find 42. Of course, this is really bad. This is a really bad idea to do that kind of stuff. Okay, in fact, this is downright a bug, and I'm going to try to show you an example here where it shows clearly that this is a bug. Okay, let's say that I have another function, sum, which takes two double parameters, which I'm going to call originally enough, double 1 and double 2. So let's say that I have here a double variable named result. Okay, initialized to 0. And after my little experience here with PTR and my function, I'm going to do something really simple. I'm going to say result is equal to sum of 42.0 and 99.0. Okay, so very basic functions. All the parameters are passed by value. I just return a simple value here. But what interests me is not the result of this function. What interests me is what happens when I call another function from the main, and therefore I create another activation record. And I do all this, I therefore overwrite the old information that was on the stack, okay, and I still try to use this pointer PTR and I dereference it in the hope that I am still able to display what used to be at the memory location of the variable TMP from the previous activation record. Well, let's see. We're going to save, compile. So, okay, undefined reference to sum. Yes, I've gone a little fast here. I didn't provide an implementation for the sum function, so let's do that. That will clarify things a little for the compiler, let's say. Double 1, double 2, and we're going to write it short. 1 plus 2 is what I want to return. And okay. Compile again. Syntactically, it's correct, except of course that the compiler warns me that I'm returning the address of a local variable. Let's try to run it. Hit a key to start. This is my in value 42. This is my in value -2. Where does this -2 come from? Well, if you do a careful runtime analysis of your program, I'm sure you can, determine it. Clearly, this kind of result is going to be It's not going to be always -2, unfortunately. This is going to be whatever is in the memory at this location. So let me try to explain to you what happened exactly here, in this case, on the stack diagram. I'm going to keep this version of the stack diagram here, and pretty much redraw it next to it. Okay, so you can have the first one for a reference comparison. So it's supposed to be exactly the same thing. Okay, system information here. PTR is here, contains the value alpha. I'm going to get to that in a second. And this is what used to be on the stack. Okay, on this side is what used to be on the stack. So I'm not going to redraw it. Okay, when I return from calling my function, this is what I had on the stack. This is the new version. I'm back in the main. Okay, ptr contains alpha, which points right here. But, you know, this is no longer a memory that is guaranteed to contain TMP. In fact, it's guaranteed to not be usable to refer to TMP anymore. So pretty much I'm kind of pointing in a wild area here. The truth is that, of course, right now, ptr points to TMP, which is still there. Its ghost image, as we called it, nicknamed it, is still there. But as soon as I call sum, what happens? Well, a new system information for that function call is pushed on the stack. The function sums has two parameters, 1 and 2, and these are doubles, so they are not, as small as TMP, for example. In fact, if you compare, what was in the memory before and what is now, let's say that TMP was encoded with 4 bytes. Well, 1 is a double. Let's say it's encoded in 8 bytes in this example. So pretty much here, in this first half of the variable, the parameter 1, you have the bits which were encoding 42 in integer encoding. Okay, but that doesn't mean much anymore because we overwrite it immediately by the 8-byte worth of bit encoding 42.0. Okay, so this half here of the bit doesn't represent 42. The encoding of a floating point number is much more complex than that. Okay, it's not half the bit for the significant digits and half the bit for the digits after the significant digits after the decimal dot. It's not quite like as simple. So when you try to look at those bits here and you try to decode them as an integer, you're going to get a surprise. You're going to get a value which has nothing to do with 42. Okay, and this is exactly what's happening here. I pass 42, I pass 99.0 to my function. I return the sum again. All this is discarded, shall we say. I'm back inside the main function. ptr is still pointing to this space. So when I dereference it again and try to read it as a pointer on integer, this is what I get. Okay, I'm trying to read what's in those bits, and I decode the ghost image of 42.0 encoded as a floating point number on 8 bytes. I try to take the first 4 bytes of that and decode it as if it was an integer. It doesn't work very well. This is what leads me to have a value of -2 displayed on the screen. So long story made short, don't do it. But now you should understand exactly why you should not do that kind of stuff.